God. Okay, we get it. We get it. All right. Oh, no. No. Oh, goodness. All right. All right. Okay. Okay. Um, let- oh, good. Um, that was it. It didn't have anything to do with learning, structural design. Okay. All right, let's get started. Real quick, I did have a mess up on my notes. I thought that the PDF that included T-beams also had doubly reinforced beams because it's not a very long set of slides, but I did not put that in the PDF, so you don't have the notes for doubly reinforced beams. Luckily, the formulas are pretty straightforward. I think we can get through the examples and everything today pretty well, and I'll have those notes for you on Friday. So I apologize for that. Homework number 5 is still due on Monday, March the 6th, and the doubly reinforced beam problem on the homework is only the last problem. I mean, you should be able to do everything else up until now. And after today, I think even after today, you'll be able to do the last one regardless of the notes. I do have to end class a little bit early today. I have a meeting in Corbly at 11, so I'm going to try and not, with all the weather, if I've got my umbrella, I'll try and not Mary Poppins all the way across campus, getting blown away. But yeah. So I'm going to end class a little bit early, but we will press on with doubly reinforced beams as much as we can. Sound good? All right, again, don't worry if you don't have the formulas and whatnot written down. I'm giving you these notes, in the not too distant future. So, okay. Let's see. So, let me sort of clear up what I mean by a doubly reinforced beam. What I mean by a doubly reinforced beam is this, okay? I mean a scenario where you have steel not only in regions of tension, but in regions of compression, okay? Now, let's be clear, for most situations, you actually don't really need steel in the compression region. I mean, in design modes, I think we understand by now that, given a rectangular beam or a T-beam or something like that, we can design a beam, and we haven't really needed to account for steel in the compression region. So it's not necessary. However, it's also more often than not there anyways. When we look at shear, for instance, I'm going to skip ahead a little bit to kind of explain what I'm talking about. Here is a typical reinforcement pattern for a reinforced concrete beam, like in total. Now we've got, this is just a simply supported beam. So up until now, what we've been worried about is selecting this bottom layer of steel. That's primary job is to resist the bending forces, okay? Now, when we do shear design, our goal is to space out these sort of hoops that are going on, going down the beam. Those hoops are called stirrups, and their main job is to provide reinforcement against shear. For instance, if you look at a shear diagram, the shears for a simply supported beam are larger at the supports than they are in the center. So if you look at the stirrups, look at sort of how they're spaced out. You've got a really, really close spacing of stirrups near the support, but out in the middle, they get spaced further apart because you don't need them. Okay. Now, structural test, you need, at the very least, you're going to need tensile rebar and you're going to need the stirrups. But just to tie everything together in a nice sort of cohesive, what we call a rebar cage, it's pretty common to put a couple pieces of rebar up top just to tie everything together. So more often than not, compression steel is there. Okay. So the question becomes, can you count on it? Well, number one, yeah, you can. You just have to be a little bit careful. Now, like I said, compression steel is there because it helps tie together the stirrups. It also, this won't really make a lot of sense right now, but later on we'll see how this comes into play. By accounting for steel and compression, you can get a little bit of a benefit on your serviceability checks later, your deflection checks. We haven't really talked about deflections yet, and we will later. You've got moments, you've got shears, but you've also got deflection checks that you have to do, and compression steel can help with your long-term deflections. Now, to compute the capacity of a doubly reinforced shape, which, by the way, we're really not interested in, at least for the purposes of this course, we're really not interested in doubly reinforced beams from a design standpoint. All I'm trying to do is ascertain if I have a doubly reinforced beam, how do I determine the capacity? Just because A, we can get a little bit of a benefit in capacity, and B, it helps out later when we look at beam columns. Now, when we look at the capacity, what? I missed something. Okay. All right. When we look at doubly reinforced capacities, we do it a lot like we did T-beams. Remember, we had two couples that we dealt with. We had the flange steel couple and we had the web steel couple. Remember that? Well, for doubly reinforced beams, we kind of have the same deal. We have the couple between the tensile steel and the concrete that's in compression, so we call that the concrete steel couple. Then we also have that force couple between the steel on the bottom and the steel up top, so we call that the steel-steel couple. So if you can get the moment capacity for each one, and again, it's just force times moment arm, that's basically it. Now, that's, in all honesty, that's actually the easy part about doubly reinforced beams. Here's the hard part. The hard part about a doubly reinforced beam is ascertaining how the compression steel behaves. In other words, let's go back to a singly reinforced beam. Basics. So we said the concrete was what? 0.85 FC prime times AB, right? And we said that the tensile steel was the area of steel times what? Fy, right? So by stating that the force in the steel was the area of the steel times Fy, we were assuming that the steel, in fact, yielded, right? Now, when we went and checked those strains, this entire time we have found that that steel has yielded. I mean, and how did we determine that? Well, we calculated the strains, right? Remember, we would say the 0.003 D minus C over C, and we would look at the strains. And we would see whether or not what those strains were to determine phi. We compared those strains against the yielding strain, they were always higher. So that assumption was always valid. For compression steel, that might not be the case, okay? Now, what we do for compression steel is we use a very similar ratio with similar triangles to determine what is the strain in the compression steel. Now, one of the things you'll find with notation is, for instance, all right, from the top to the tensile steel, we call that D, right? From the top to the compression steel, we call that D prime. And the area, we call that area of steel prime, okay? The strain in that steel is epsilon sub S prime. Anytime there's a prime, we're talking about the compression steel. Sound good? And don't worry, I know y'all don't have the notes, but the formulas, you know, it'll be pretty straightforward when we go through the examples. Now, to calculate the strain in this steel, it's again similar triangles. We take 0.003 is to C as whatever this strain is to C minus D prime. Does everybody see that? So it's just another set of similar triangles to determine what is the strain in that steel. And what we may find is that compression steel might yield, and it might not, okay? Now, if it yields, it's simple. The force in that steel is just the area times Fy. But if it hasn't yielded, then it's a little more complicated than that, okay? I propose that if it hasn't yielded, then the force in that steel is the area times whatever the stress is. And you're going, well, what do you mean whatever the stress is? Well, let's keep in mind we are assuming a stress-strain curve that kind of looks something like this. So here's our stress, here's our strain. And we're assuming a stress-strain curve that's linear up until Fy, right? So this slope is what? That's the E for the steel, right? So if my strain is lower than epsilon sub y, and I want to determine, you know, some point on this curve, some F sub s, how would I determine that? I'd say it's the E times whatever the strain is. Does that make sense? Everybody okay with that? Now, what's going to happen is this. So I have the area times whatever the stress is, which is E times whatever the strain is, and the strain is 0.003 times our similar triangles relationship we just developed. Everybody with me so far? Yes. It will be. It will be. It will be. What's going to happen is if I take this term right here, plug it into C equals T, start rearranging everything, I get a quadratic equation in terms of C. Now, I know you're seeing this and going, oh, goodness. This really is about one of the most plug-and-chug expressions that we use. The big thing to keep in mind is you have to do the check to see whether or not the strain in the steel is above or below strain at yielding. And if you're going, wait, this is a lot of math, don't worry. It isn't so bad. Everybody with me so far? Don't worry. We got plenty of examples that'll make our lives a little easier. Let's take a look at one. Okay? So I have here a beam. It is, let's see, it's 14 inches wide. The depth from the top to the bottom of the top to the tensile steel is 24 inches. From the top to the compression steel is 2.5 inches. So I'll write out this these terms here in a little bit. We have 2 number 9s for compression steel, so the area is 2 square inches. And the tensile steel, we have 4 number 11s, so it's 6.25. Don't worry, I'm gonna draw all this out. So if you're sitting here copying down all these values, don't worry, I'm gonna draw all this out. Is everybody okay so far? We're going to compute the design capacity, and I think you'll see this isn't so bad. Okay. Okay, so example, oh goodness. Example 11A. Okay, so first off, we're going to need some material values. Is what? Oh, no. First off, okay, FC prime. FC prime is 3 KSI, so regardless, we know what beta 1 is, and it is? There we go. Now, FY is 60 KSI. Now, what that tells us is that the strain that is required to generate yielding is F sub y over the Young's modulus, which is 60 KSI over what? Not bad. All right, so help me out. What does this come out to be? All right, I'm going to carry that out one more and say 207 because that'll actually matter here in a little bit. Okay. Everybody okay? All right. Now, let's draft out the beam and let's do some C equals T and let's see what we get. Okay. So the first thing that we're going to do is assume, so maybe I ought to do this. Maybe I ought to put the big assumption here. Assume compression steel yields. All right, so let me explain what I mean by that. Now, let's look at the beam. So here's the beam. So the first thing that we know that B, which is the width, is 14 inches. Okay. Now on the bottom, we've got 4 number 11s. Okay. So 4 number 11s, and this is an area of steel of 6.25. Everybody okay with that? Now, the D distance from the top to the center of that steel is right here, and that is a D value of 24 inches. Okay. Everybody with me so far? Now, let's also be clear on a couple things, okay? Let's just assume that there's no steel right here. So what would we do? We'd say C equals T, and we're trying to figure out how deep that stress block is, right? Everybody with me on that? So we're still going to need to do that, but I have to recognize that I've got a bar here and a bar here, okay? And these are two number 9s, and this is an area of steel, but we call this an area of steel prime of 2 square inches, okay? And this distance right here, on the left, is from the top to the tensile steel. On the right, it's from the top to the compression steel, and we call that D prime. And that is a D prime of 2.5 inches. Sound good? All right. Still the same goal as it was before. We're going to have some stress block, something like this, some region of the concrete that is in compression, and we need to determine what is the depth of that region such that C equals T. Okay? So let me do this. This is D prime is 2.5 inches. So we still have the same question, A equals something, okay? So we go back to our fundamental equilibrium. Everything in compression has to equal everything in tension, all right? But because we've got compression steel, we've got two components to compression. We've got the compressive force in the concrete plus the compressive force in that upper layer of steel has got to equal the tensile force in that steel down below. Everybody okay with that? Everybody with me so far? Okay, now, here's the thing. Let's take the tensile steel. I mean, how do you find the force in the steel in tension? You take the area times Fy, right? I'm going to also do the same thing here. I'm going to assume it's the area times Fy. That is an assumption I'm going to have to verify, okay? But we'll see how that goes here in a second. All right, let's just fill in each one of these. The compressive force in the concrete, I propose that is 0.85 FC prime AB, just like it always was, okay? But I've also got an additional compressive component. I've got the area of steel, the compressive steel times Fy. And that's got to equal ASFY down below. Everybody okay with that? Okay, so what in that equation do we not know? A, we know everything else. We know the areas of the steels, the material properties. B, we know everything else. The one thing we don't know is A. Okay, so let's solve. So what does A equal? Well, if I take this and I bring it over, I'm going to have ASFY minus AS prime times FY, right? So I can factor out the FY and I'd have AS minus AS prime times FY. Everybody all right with that? So I've got AS minus AS prime times FY, 0.85 FC prime B. Everybody okay with that? Okay. So let's plug and chug and let's see what we get. So we've got 6.25 square inches minus 2.00 square inches times 60 KSI over 0.85 times 3 KSI times 14 inches. Somebody help me out and tell me what you get. 7.14, like 3. Second on that? All right. Okay. Now that's A. Okay. Let's calculate a little C right now and just say C is A over beta 1, which is 7.143 divided by 0.85, and get what? 8.403. Okay. Is everybody okay with this so far? Everybody happy so far? Okay. Now, here's the thing. That calculation for A, okay, it is only valid if this steel has yielded, okay? We made an assumption when we plugged in Fy right here, we made an assumption that that steel had yielded, okay? We have to verify that assumption. The way that I'm going to verify that assumption is I'm going to compute the strain in that steel, okay? And I'm going to do that by saying that the strain in the compression steel is 0.003 C minus D prime over C. And yes, it is C minus D prime, not D prime minus C. Although it doesn't really matter, all that's going to do is change your sign. Okay? 0.003 is to the C as whatever that strain is to the C minus the D prime. All right? So let's plug and chug and let's see what happens. So 0.003, we have 8.403 inches minus 2.5 inches divided by 8.403 inches, and we get something. What do we get? Okay, 0.00211. I got a second on that? Okay, 0.00, what? Did somebody, did we? Thank you. 0.00211. Now, what does that value mean? Okay, let me ask it like this. That is the strain in our steel, assuming that it has yielded. How much strain is required for it to yield? 0.00207. So this quantity is greater, I'll say it's greater than 0.00207. What does that mean? It has yielded. Our assumption is valid. Is everybody okay with that?
So it got shorter? It's yielded?
Yes, it got shorter and it breached Fy, or epsilon sub y. So right here, this means our assumption is valid. Oh goodness, getting ahead of myself. All right, so the compression steel did in fact yield, okay? So that's what that tells us, okay? Now while we're computing strains, we might as well compute the strain in this steel. Now why do we need to compute the strain in the tensile steel? Exactly. We need to know what phi is, and we need to know what the ACI, if we've met ACI requirements. So let's see what happens. And that's computed the same as it always is. Epsilon sub s is 0.003 d minus c over c. So 0.003, 24 inches minus 8.403, 8.403. And so what does this come out to be? All right, 0.00557. Do I have a second on that? So what does that mean? There we go. Bless you. So I'm just going to put phi equals 0.9 just for our purposes. But yes, it does meet our ACI requirements. Okay. Everybody okay with this so far? Okay. Bless you. All right. If you're if you're okay with this, then we can compute our moment capacity. Bless you. Goodness. Wow. All right, hold on. I'm losing track of what I'm talking about. This is 11, 11A. You mean how great it is to discuss doubly reinforced concrete sections, right? Okay. Whoa. Wow. Just wow. Okay. All right, all right. So, all right. To compute a, now hold on, let's get back on track. Okay, to compute a moment capacity, we need two things. We need forces and we need distances, okay? Now, just like we did with the T-beams, I'm going to focus my efforts on the forces in compression. And I'm just going to sum moments from the tensile steel. So that force times that distance, that force times that distance, and just add them up. So let's start off, let's compute each of those forces. So we have a C sub C, which is 0.85 FC prime AB. So let's check that out. So we have 0.85. FC prime is what? 3 KSI. What was A? There we go. And B is 14 inches. Okay, so plug and chug and tell me what you get. 255? All right. Now, what is C sub S prime? Well, we assumed that the steel yielded, and we found that we were, in fact, correct in making that assumption. So I propose it is just the area of steel in compression times Fy. So the area of steel in compression is 2.00, whoa, I don't need that many zeros, 2.00 square inches times 60 KSI. And what? Okay, yeah, that is 1 point. Oh, no, it's not. It's Kip's. But I want it to be inches squared.
We gave you a pass with one mistake today.
You can't let that one. No, yeah. But I am writing the units out, so it was easy to diagnose that there was a problem. I'm writing out the KSI and the inches and all that. Now, on the side, I do want everybody to do this, so note. Okay. All right, we get it. All right. Now hold on. The tensile force is the area of steel times Fy. I want to compute what the force is in the tensile steel. So what is the area? No, the tensile steel. That's the 6.25. And that's 60 KSI. And what do we get for T sub S? 375 kips. Now, why did I do that? To see if they're equal to one another. I wanted to verify that C equals T. And if I add up the C, I get 255 plus 120, I get 375. So I really recommend that you do that. I know it's not necessary, but I recommend that you do it to ensure that you haven't messed up something in your calculations and that C does in fact equal T. Okay? Does that make sense? Okay. All right. If you understand that, then to get the moment capacity, it's pretty straightforward. Okay? Does everybody have this written down? Because I actually want to refer back to the previous slide. Okay. All right. Tell you what I'm going to do. Okay. So here's the beam. I'm going to sum moments from the tensile steel. Okay. So the moment capacity is going to be a force times a moment arm. So nominal moment is going to be that compressive force in the concrete times some moment arm plus the compressive force in the steel times some moment arm. Now, because I'm summing moments right here, the moment arm for the tensile steel is 0, so I don't have to worry about that. So let me ask you this. How far is it from the tensile steel to the center of this compressive block? The compressive block. So we go up D, down half that, right? So maybe what I ought to do just to reduce confusion is say that this is 7.143. But that is correct. It's D minus A over 2. And that's exactly what it was before. It was, you know, or ASFY times D minus A over 2. Same thing. Okay? Now, here, the compressive steel, how far is it from the tensile steel to the compressive steel? D minus D prime, exactly. So, there is your moment capacity for a doubly reinforced beam, in a nutshell. So, this is an important one, yes. Now, hold on. We're going to get back to that. We'll get back to that. Hold on. All right, so 255, now hold on. 255 kips times 24 inches minus 7.143 inches over 2 plus 120 kips times 24 minus 2.5 inches. Now, Mr. Crookshanks, you had a number for us? 7789.3. The number doesn't mean much if it doesn't have units associated with it. So what are the units? They're not inches squared. Inch kips. We have kips in inches. So if I wanted that in foot kips, divide by 12, and what do we get? All right, so that's MN. Phi MN is 0.9. We determined phi earlier. Now, give me a second. So what, 584, we'll just keep it simple, 584.2? No, it's not. That's a dot product. Okay. So there's your answer. There's your design capacity. Okay, does that make sense? Hey. That's a good question. What if it hasn't yielded? He's on to something.
I didn't know there was an 11B because I didn't have
What's that? No, that doesn't count. That doesn't count at all. Because if there's an 11A, I mean, come on, there's going to be an 11B.
Well, I mean, us not having the doubly reinforced handout.
I said that counted as a mistake. I even owned it.
I don't remember.
I did.
So many mistakes now. I can't keep up.
It's only 4, though.
Can we bring his cake when we celebrate your birthday 2 days late on Friday?
Guys, come on. I know, well, no, it's not.
Yeah,
No.
it was more like, we're going to go ahead and ask for forgiveness.
I'm not going to stop you all from having cake if you want to have cake. So I'm going to be teaching, though, so I'm not going to be going, show the doubly reinforced compression. Not going to be doing that.
So you want to eat cake if we gave it to you?
I'm going to be teaching. All right. Now, here's example 11B. Now, if you look at example 11B versus 11A, they're very, very similar, except for the fact that a few dimensions have changed with respect to the steel. We have 4 number 10s, and we have 2 number 7s here. And we also have different material grades. We have 4 KSI concrete as opposed to 3 KSI concrete on the last example. It might not seem like enough, but we're going to find a different result. Okay? Sound good? Yes.
Something I'm noticing with the reinforcement is they look on the circles look a lot bigger now.
I really think that
From A to B, but from like now to like way back when we were just doing the bottom reinforcement.
I wanted to emphasize more and more throughout this semester that there's rebar there. So triple exclamation point rebar. That's what that is. Okay. Now let's sort of at least set up some basic calcs, and then we'll sort of call it. So this problem is going to start out just like the last one. Okay. So I'm probably going to refrain from drawing a lot of the diagrams because they're all the same. So example 11B. So we're going to make the similar assumption. We're going to assume the compression steel yields. So we still have the same base equation that we had before. C sub C plus CS prime equals TS. So that's 0.85 FC prime AB plus AS prime FY. And then that has to equal AS FY. So over here, maybe what I ought to do is I might say, all right, B is, I think, hold on, let me go back to the slide. B is 14 inches, D is 24. What's that? No, that's a good question. But that's from steel to steel. From the top, that's that extra 2.5. That's a good question. No, that's a... Guys, come on. All right. AS and AS prime. So AS is 5.06 and 1.20. 5.06 and 1.20. This one, right I do. Thank you. Okay, all right. I'm going to finish this and I'm going to call it. All right, so just like last time, we're going to solve for A as AS minus AS prime times FY, I'll make parentheses right there, 0.85 FC prime B, which is 5.06 minus 1.20, 60 KSI, 0.85, 4 KSI, 14 inches. What do we get? Maybe like 6.6? Okay. All right, C is A over beta 1, which is 4.866 divided by 0.85, which comes out to be what? 5.724. And epsilon sub S prime C minus D prime over C, so 0.003, 5.724 inches minus 20, or no, that's 2.5 over 5.724 inches, and what do we get?
0.0017.
Like 169? So now we're using the same steel in the last problem, so the yielding strain is 0.00207. So we made an assumption that the steel yielded, and that assumption was in fact invalid. So we're going to have to handle this problem a little bit differently. So this is less than 0.00207. So assumption is invalid. So we're going to have to handle this one differently. Specifically, how we handle this will be the subject of discussion for Friday. Cliffhanger. This is a cliffhanger. All right. Does anybody have any other questions? All right. I do have to go, so I'm going to stop class now. I will see you all on Friday.